ThermoFire is a sister project of Furious. We were both founded in the CBE call of 2022. And on the other side, Furious has presented different and is aiming different applications and different functionalities in the bio-based polymers that you are developing. In our case, we are really much focused in the fire performance of the fibers and the composites that we are developing. So the title of our project is Bio-based fire-retardant thermoplastic composites reinforced with natural fibers. This project, I'm going to present the general introduction and the objectives. Then I will briefly have an overview of the materials that we are developing until the date, which is the polyamide 11, the fibers, and the flame retardant additives, and of course, the integration of all of them in a composite, showing the preliminary results that we have up to the date. ThermoFire is aiming to design, develop, and validate novel, lightweight, and low-cost bio-based and recyclable thermoplastic composites with mechanical properties and mainly fire resistance by the incorporation of natural fibers and bio-based allergen-free flame retardants. So we are aiming a 100% bio-based polyamide 11, the bio-based flame retardant, and the bio-based fibers, having at the end a 100% bio-based flame retardant composite for different applications. We are aiming 3 prototypes in automotive, aerospace, and textile sectors, and the final objective is remove the European dependence on the fossil-based polymers, increasing the sustainability of the composites. You can see here the type of prototypes, the use cases that we are aiming. In the first part, we are aiming to develop by prepreg techniques composite for the aircraft seats. So we have to validate the flame retardancy and also the mechanical properties for this use case. We are also aiming some automotive components, like for example, the electrical vehicle housing of the battery. And in the last but not least, we are aiming insulator panels for building and also for automotive sector made of 100% bio-based composite. So these are more or less our numbers. We are near to 4.5 million euros of contribution from the CBE, and we start in June 2023. We will last until May 2027. Here it's a bit the consortium. We are 2 research and technological centers, 6 SMEs, and 4 large companies focused mainly in the south of Europe. And as I commented before, the main objective of this project is the 100% bio-based composite, but also aiming a 20% reduction in weight in the applications and a 30%, around 30% in the cost, while we are able to maintain the required levels of safety in the different sectors that we are working with. So all the materials that we are going to use, I'm going to present then the results, are allergen-free and bio-based flame retardants with low toxicity if we compare with the commercial or the state-of-the-art. All of them are environmentally friendly and low-cost fibers based on cellulose, as reinforced with CO2 neutrality, directly extracted from nature without further processing. We can see here a graphical scheme of how we are working with. I'm going to explain. Arkema is our partner leading the development of the bio-based polymer, in this case the polyamide 11. We have Canoe leading the preparation of the natural fibers, mainly cellulose and flax, and Avanzare ourselves leading the preparation of the bio-based flame retardant materials. Then we will have to scale up the formulations, working together CTME and Natureplast, and in collaboration with the Technological Food Sector Center of La Rioja and also the industrial partners which are preparing the use cases, Safran in the case of aerospace, Stellantis in the case of automotive, CRF, and in the case of the textile, the non-woven fabrics, we have a Geopan. So then at the end, last but not least, of course, we will test the recyclability and the life cycle cost and the life cycle analysis. If we focus first on the flame retardant additives that we are using, we are focused on phosphorus-based materials, nitrogen-based, and some of them, for example, are the molecules that you are seeing here. We typically obtain from biomass or from other natural resources. If we focus on these, some examples that we have tested until the moment, for example, in the case of phosphorus-based bioflame retardants, is the phytic acid that can be obtained from plant sources, And in the case of nitrogen-based, we are working with lignin and tannins that we can obtain, for example, from the grapes. We are also combining this type of bio-based flame retardants with other materials, carbonous materials, prepared by Avanzare from natural graphitic sources. So from natural graphitic sources, we can prepare graphene oxide and nanoplatelets. Why we are combining the materials, the bio-based flame retardant additives with this carbon material? Because we know that we can produce a charring effect. What is a char? A char is a layer which stays between the polymer and the flame and protects from the fire. How does it protect? If we take a look in this graphical scheme, when a flame reaches a polymer, it creates the heat, decomposes the polymer, and creates the volatiles. These volatiles from the polymer feed again the flame and increase again and again the fire, releasing in the gas phase products as carbon dioxide or monoxide. Okay? So when we create the char, which is this represented here, this black layer, we protect the polymer by three types of mechanisms. What are these mechanisms? In the first part, we reduce the volatiles because we are protecting, so the flame is not arriving the polymer, so we reduce the volatiles and reduce the flame feeding. In the second, we reduce the oxygen permeation, so we are reducing in the second part the flame, and in the case that we are putting, for example, materials with high thermal intrinsic conductivity, as the case of graphene nanoplatelets, we are achieving a re-radiation of the heat of this flame. So we are currently achieving a protective layer and a stable layer, a char, which is very stable and protects effectively the polymer to the flame. How we can see this graphitization that we are obtaining, for example, if we see this Raman microspectroscopy, the materials before and after the fire, we can see this D band associated to the graphene defects material, which has been reduced significantly, and also the G band has been narrowed a lot because the reducing effect of the flame in the graphene oxide. So this type of materials, graphene oxide, together with chitosan or with other biomolecules and the graphene nanoplatelets can improve significantly the results that we are obtaining. I put here the classification of the materials that we are obtaining. It's a classification according to the UL94 because we are going to show some of the results that we are obtained until the moment. This is some of the characterization that we do over the graphene oxide and the nanoplatelets that we are using. You can see that the morphology of this material is a planar morphology with a lateral size between 5 to 40 microns in plane and less than 10 microns of thickness. In the second part, what Arkema is leading is the preparation of a 100% bio-based polyamide 11 using a renewable source, which is the castor oil, and moving not only to have a bio-based, but also we are including some biomolecules which can retard the fire retardancy, the fire mechanism of the polyamide into the polymerization of the monomers. So as you can see here, some of the results that we have obtained in this experimental matrix working with the bio-based polyamide 11, nanoplatelets, and the tannin, chitosan, it's, if we compare with the neat polyamide, you can see that according to the UL94, the test that we are doing self-extinguish in 0 seconds, so are classifying near to V0, although what we are doing now is controlling the dripping of the polymer, adjusting. This is why we are adding this other column, working with rheology adapters to have a good performance as much as possible and to adapt to the use cases that we are preparing. You can see that after 10 seconds of flame application, the material self-extinguishes in 0 seconds. Okay. The second thing that we are putting our flame retardants on, sorry, it's the fibers. We are using cellulose fiber or jute, hemp, or flax fibers to have reinforcement in our polymer. So what we are doing is activating the surface of the fibers to a pH about 4, and then we are putting our flame retardants in suspension creating this protective layer in the fibers. So we are increasing as much as possible the charge of these bio-based flame retardants and have a short process to dry at a low temperature our fibers. If we see here the performance of a non-treat fiber against a treat one, you can see in the video the difference, because this one, which has not been treated with any flame retardant, is completely burned in less than 10 seconds, and the treat one resists the 2 applications of 10 seconds with a direct flame without spreading the flame or without having any dripping. So here it's more or less so far where we are now. We are testing, as we say, the synergy between the different carbonous material and how we can adapt the rheology to avoid the melt dripping of the polymer. We are testing the synergy between the different flame retardancy and the carbonous materials to increase the performance and adapt to the use case requirements. And of course, when we have all the selection of the materials, we will prepare the composite with the treating additives, the fibers, and we will test and validate the properties, bearing in mind always the cost and the life cycle analysis. And I think this is everything from our side at the moment. Thank you.